organizing this. When Andrea contacted me sometime late last year about doing this presentation, I said yes right away because I have family in the area. I visit this place quite a lot. And so I thought, why not? The other thing I would mention is also that there's a lot of research that shows, that indicates that the best thing you can do about climate change is to talk about it. And so, what I'm going to do today is give you a quick overview of what my research is about. So I'm a physical climate scientist, and what that means is I study how the climate system works. I use computer simulations to figure out how climate is going to change in different parts of the world. And so today's talk, what I thought I would do is, so I thought I would try and answer four key questions that we all think about. The first question is, how can we be so sure that the climate is changing? And so what I want to talk about really is that the climate system is changing rapidly. And I'm going to give you, talk about some recent observations that help us understand how fast the system is changing. Question two is, how unusual are these observed changes? So what I'm going to talk about is, the global temperature has risen by about 1.5 degrees Celsius, so 2 degrees Celsius. Why do we care about those small changes that are happening in the system? The third question I will answer is, why is the conversation centered around regulating or reducing CO2 emissions? So all our conversation globally right now is about decarbonization, right? We want to somehow figure out a way to reduce our carbon emissions or remove carbon from the atmosphere. Why do we focus so much on carbon dioxide? And then finally, I'm going to talk about how climate change is affecting us here in New England. And that's where I'll talk about some of my research as well. So many of you, so the first question, how can we be so sure that the climate has changed? And what I'm going to do is talk about the indicators of climate change. If you were to go on the NASA website or National Oceanic Atmospheric Administration website, what they talk about are these indicators of climate change. There are certain measurements that are done worldwide that tell us how the climate is changing and how fast it is changing. And so the first plot I'm going to show you is this, and I'm sure almost all of you have seen some version of this plot. What you see here is how global average temperature has changed from 1850 up until now, 2020. So this is the latest report on global warming. And it tells you, the first thing you can see is that it's quite clear that the global average temperature is increasing over time. But there are lots and lots of interesting information in there. The first question is, how do we know how the global average temperature is changing? And so this information comes from thermometers all across the world, right? Essentially, scientists are going out collecting thermometer information from all around the globe, and then they're processing that data to create a graph like this. There are different lines in different colors on this plot, and that is telling you how different scientists or agencies around the world are collecting that data, processing that information, and independently creating their own global temperature records. And so you can imagine that it's a really complex and tedious work. Sometimes, we have thermometers that were in rural areas 100 years ago, and then the development happened. Now it's an urban setting, and you have to make corrections to those thermometer settings to make sure that the change in urbanization is not affecting your temperature. So sometimes thermometers break, and you have to replace that with a different thermometer that might have a slightly different sensitivity, right? So all of those measurements that we collect from around the globe need to be homogenized. They need to be processed before you can produce something like this. And so there are many different agencies around the world. Hagley Center in the UK, GISTEM is the NASA agency. That's NOAA, the National Oceanic Atmospheric Administration, and ECMWF is another European agency in Germany. They all independently collect all that data and create the record of global average temperature. And you can see that for any individual years, there are differences between those estimates. But overall, all of those records tell you that the globe is warming. The other thing I'll point out is what you're trying to see here is these are not absolute temperatures, but these are called global temperature anomalies. That means you are trying to measure or report the temperature of any given year relative to a certain baseline. And this baseline here is this period 1850 to 1900. And so we consider that 1850 to 1900 period as our pre-industrial baseline. That means that's the time when we hadn't emitted a lot of greenhouse gases in the atmosphere. The temperatures were more or less stable. They varied quite a bit from year to year, but they were stable. And since we started emitting more greenhouse gases, the temperatures have gone up. And last year was the warmest year on record. If you were to consider this 170-year record, the last year was the warmest year. And the temperature was about 1.5 degrees Celsius higher than the previous year temperatures. Now, that's showing you global average temperature. This is how it looks across the entire globe. So not every part of the globe is warming at the same rate. What you see here is all the regions that are in red are the regions where the temperature is going up rapidly, right? And many of you might already be looking at the Northeast region. It's in dark red, and it's one of the fastest warming regions around the world. And I'll talk a little bit about that. But in general, our observations tell us that the land areas across the globe are warming faster. Oceans are warming as well, but slightly at a slower rate. And that's because water takes a lot more energy to change its temperature. And so naturally, it's warming at a slightly slower pace. So that was the first indicator that it, right? The global average temperature. The second thing I want to talk about is the ocean. So on an average, the global temperature is going up, but our oceans are also accumulating more and more heat, right? So what you see here is the record for the ocean doesn't go as far back as that for the temperature because it's very hard to monitor what's happening in the ocean. But since the 1970s, we have satellite data that is looking down into the oceans and figuring out how the ocean temperature is changing. And what it clearly shows you is that the top 700 meters of the ocean has gotten warmer. It has accumulated more heat. And you can go down to about 2,000 meters, and that also shows that the ocean is warming. So ocean is not just warming at the surface, but it's also warming at depths. And essentially what's happening is that extra heat that is trapped by greenhouse gases is absorbed at the surface, and ocean circulations take it down into the deep ocean. Once it gets into the deep ocean, it can stay there for a very long time. And in general, since ocean is a very big reservoir of heat, about rather more than 90% of the excess heat that the greenhouse gases are trapping is going. And that's another clear indicator that our system is accumulating. Now, you might ask, how do we know so much about the ocean, right? And if you go back a few decades or 100 years, those ocean measurements were pretty rudimentary, right? People were essentially just ships as they traveled across the world. They would just drop buckets, fetch water, stick a thermometer in, and find out what the temperature is. That's clearly not enough to map out how the global ocean is changing. And so what we have now for the past about 22 years are these Argo floats. So you can see the size of those floats. They're not really big machines. They're like tiny floats that you can just drop in the water. What they do is they go up and down to depths of about 200 meters. Okay. I'm going to try and stay close to the projector because people online cannot hear me. So I won't move to the screen. But But those Argo floats are these machines that go up and down. As they go up and down, they measure temperature, salinity, other chemical properties of the ocean. They relay that information back to satellites, and then we can get that information easily. What you see on the top right there are the locations of all the Argo floats that we have available right now. And those different colors indicate countries that are responsible for deploying and maintaining those Argo floats. So essentially, it's a really big coordinated, global coordinated effort to monitor what's happening. And that's what helps us understand how the ocean is accumulating heat that I showed you on the previous slide. The third indicator is the cryosphere, right? We have lots of ice all across the world, and that ice is responding to changes in air temperature as well as ocean. On the top left, you see, I'm showing you a figure for Greenland and Antarctica there. And that figure indicates the ice sheet height in those places. So anywhere you see red colors on the top left-hand side, the smaller panel on the left-hand side, in those areas in Greenland and Antarctica, the ice sheet is about 3 miles thick, right? It's a massive ice sheet. If you were to melt all the water that is locked up in the Greenland ice sheet, it would raise sea level by about 5 meters, or roughly 15 feet all across the world. If you were to melt all the water that's locked up in the Antarctic ice sheet, that would raise the global sea level by about 50 meters, 150 feet. There's a lot of ice in those ice sheets, and I see concerned faces. So I'll just say that we don't have to worry about that. It takes a very long time to melt those ice sheets, centuries, thousands of years. At the same time, it also takes a very long time to build those ice sheets. So once we melt them, they're not going to come back on the time scale. And that's what we are concerned about, right? The middle top panel is showing you areas where these ice sheets are losing mass, right? So anywhere you see red colors is where the ice is melting and is flowing into the ocean. And that's what the bottom panels show as well. We've been measuring ice sheet mass loss for the past 20 years, because now satellites again can monitor those areas very nicely. And so we have a really nice picture of how these ice sheets are losing mass. Once that water flows into the ocean, you can imagine what's going to happen, right? The sea levels are going to go up, and that's what we see as well. So this data set is based on tide gauge measurements. People are going out to the beaches and figuring out what the sea level has been over the last, again, 140 years. And it's quite clear that the sea level is going up, and it's going up at a faster rate now than it used to a few decades ago. Now, the sea level, rising sea level, that picture is complicated because there are two factors essentially that contribute to the rise in sea level. One is, of course, the melting of all that land ice that flows into the ocean and raises sea level. The other one is the thermal expansion of the ocean itself. As I mentioned earlier, the ocean is getting warmer, and as it gets warmer, that water expands, and that also leads to higher sea levels. And so the sea level rise that we've experienced so far, half of that has come from the expansion of ocean water, and the other half comes from the melting of all the land ice. And you see a really striking picture at the bottom where there's one glacier in Alaska that has completely disappeared, creating that lake, and then eventually that water will flow to the ocean. And so what I've just talked about, these indicators of climate change, right? These are all independent measurements, right? Increase in air temperature, that's based on thermometers. Ocean warming, those are based on that data. They're based on Argo floats. Then you have sea ice. I didn't talk about that, but the sea ice is going down as well. That comes from satellites, sea level rise from tide gauges, and ice sheet mass loss. All of these are independent measurements done by independent scientists. They all point in the same direction, that the climate is changing And they all show us a consistent picture. And that's the reason why we are so confident that it's changing and we need to do something about it. And so the global effort, right, you must have heard about the Paris Agreement that happened in 2015. What was agreed in 2015 was a major global conference. 195 countries came together to talk about what we can do about climate. And one of the agreements was that we want to hold the increase in the global average temperature to well below 2 degrees Celsius. And we should pursue efforts to limit the temperature rise to 1.5 degrees Celsius above the industrial levels. So what I want to talk about is why are those numbers important? And you might have heard about, you might have seen this in the news, right? Since the last year was the first year in the recorded history to cross 1.5 degrees Celsius, it was all over the news. World's first year reach of 1.5 C limit, temperature rises past 1.5 C for the full year. And then you see apocalyptic pictures like that go along with the news. Now, the 1.5 C or 2 degrees Celsius target, those targets are meant to tell us about times when the temperature remains above those levels. We haven't reached that stage yet. We are moving in that direction, but we haven't reached those temperature levels yet. But what I want to talk about is how unusual are these changes and why should we care? And to understand how scientists came up with those numbers, right? 2 degrees Celsius or 1.5 C, we need to look at the Earth's climate history. And Earth's climate history tells us about why those numbers are something we should be concerned about. And it's a field called paleoclimatology that helps you understand how Earth's climate has varied in the past before we started keeping systematic records. The way we do that is you can look at indirect ways of understanding what the climate was by looking at geological structures, chemical records, biological records. And here's just one example. So for example, trees outside, mostly in the mid-latitude regions, have tree rings, right? Many of you must have, if you go out for a walk in the woods and see a fallen tree, you might be able to see the rings on those trees. And those rings can be studied to understand past climate history. Trees grow one ring per year, and the distance between how wide that ring is or what the color of that ring is determined by the temperature and moisture conditions at the time of the formation of that ring. And so as you are going towards the center of that ring, you're essentially going back in time, and that helps you reconstruct Earth's climate. There are many other records in the environment that indirectly tell you about the climate of the past. And so I'm not going to spend more time on that, but I'm just going to show you some results there. So this is the famous hockey stick diagram, and it tells you how the Earth's temperature has varied over the last 1,000 years, right? So the global temperature record that I showed you earlier is just that last flip, the red in the red that you see at the end, right? And it's quite clear, looking at this, that the current temperatures that we are experiencing, the Earth has not experienced those temperatures in the past 1,000 years. Just want to tell you a little bit about these three scientists there. This was published in 1999 by Michael Mann, Ray Bradley, and Malcolm Hughes. And many people did not like this result, especially people in Congress did not like this because it meant, it showed for the first time that humans are responsible for what's happening. And after that study was published, these scientists who produced that result, they were harassed by politicians in Washington. Raven Bradley was my PhD advisor, and when I started working with him, my PhD, he was actually going through a congressional inquiry at the time. Congress essentially made them, all of these three scientists, make their emails, all their communications, all their research public, and they set up independent teams to see if this result was fabricated. Eventually, those independent scientists came up with the same result, right? But this was harassment. Ray Bradley ended up writing a book, Global Warming and Political Intimidation, How Politicians Track Down Scientists as the Earth Heated Up. It's just basically wasting scientists' time. You have the longest serving Senator James Inhofe on the left, bottom left there. And that picture is from 2015. He ended up bringing a snowball in February, Senate floor, just to say that, okay, since it has snowed outside, global warming is a hoax, right? So there is an effort. We all know that that's an idiotic comment, right? But people are actually doing this. Companies are pouring money into disinformation campaigns, and that's the reason why we still do not have that there. But over the years, many scientists have worked on creating that graph, and we have reproduced it well. But that's just going back 1,000 years, right? Can we go back even further in time and figure out how the climate has varied in the past? And these ice sheets that I was talking about in Greenland and Antarctica, they give us clues about how Earth's climate has varied for thousands of years. If you think about Antarctica, Antarctica is actually a really arid place. It's a really dry place. Moisture doesn't get there very easily. And so if you were to think about building an ice sheet that is 3 miles thick, it takes millions of years. That ice sheet formation started about 3.2 million years ago. And since then, slowly, that ice sheet is being built. So what you can do is you can go there, you can drill down into the ice sheet, you can recover an ice core, and that is going to tell you, because those layers in the ice sheet are going to tell you about the past climate. So I'm going to show you the result that you get from that ice sheet reconstruction. What you see here is the record of how global temperature has changed over the last 400,000 years, right? Our current climate is on the right-hand side, and then you go back 400,000 years towards that. And you see there are fluctuations, right? For the past about 10,000 years, the climate was relatively stable. Then it started getting cooler. So if you consider today as 0, then you can imagine that if that red curve goes down, that means colder climates. If it goes up, it means warmer climates. And you see this periodic structure there. And what that tells you is that the Earth's climate has varied between 2 different states. If you consider the current state to be 0, about 21,000 years ago, our global climate was colder by about 4 degrees Celsius, right? Only about 4 degrees Celsius, but that meant a very different world. And I'm showing you that right below where we are sitting today, this area was covered in ice, a mile-thick ice sheet. And that's not just snow, right? That's ice that was present here through summers, through winters for thousands of years, right? The entire North America was covered in ice, and so was northern parts of Eurasia, right? So that's a very different world. The geography looks really different, and that's just 4 degrees Celsius change in temperature, right? It takes a long time. We're talking about thousands of years to make those changes, but 4 degrees Celsius can make a huge difference. The other thing we can do using those ice cores is extract out air bubbles that are trapped in those ice cores and learn about the past chemical composition of the atmosphere. Because what happens is as the ice accumulates, it traps air bubbles as more ice falls on top, and eventually it becomes the compaction leads to trapping of air bubbles in those different layers, and those air bubbles have ancient air that is completely isolated from the environment, and you can just extract that air bubble and learn about the atmospheric chemistry. And you can see that the green curve there is showing you how carbon dioxide has varied over the last 400,000 years. Again, when we have colder climates, the carbon dioxide levels were 180 parts per million. Lower when we had warmer climates, they were higher, right? So temperature and carbon dioxide go together. And then the final thing is you can also add a picture about how sea level has varied, right? So if you are building a massive ice sheet here in New England, all across North America and Eurasia, that water has to come from somewhere, right? And that water essentially comes from evaporation in the ocean. You take that water, you dump it over land in the form of ice, and you lock it up in the form of ice sheet. And so every time you have colder conditions, this was about 21,000 years ago, the sea level was down by about 100 meters or 300. 21,000 years ago, temperature was 4 degrees Celsius cooler, and the sea level across the globe was down by lower by about 100 meters or 300. Now, it's hard to imagine that, right? It's hard to imagine that, so I'm showing you a picture of Florida right here. This is what it looks like today, right? The rightmost panel shows you what Florida looks like today. The middle panel shows you what it looked like 20,000 years ago, right? You could walk 100 miles off the coast of Florida because the ice level had fallen by about 100 meters, because all that water was evaporated and locked up. So 125,000 years ago, when the climate was only about a degree warmer than it is today, much of South Florida was underwater completely. And that's because you melted all those ice sheets and you put that water back into the ocean. Now, of course, these changes take a very long time, but what I'm trying to emphasize here is that small changes in temperature can make a big difference in our climate system. And if you didn't notice, what carbon dioxide concentrations are doing right now, there is that the green curve spikes up at the end, and that's where we are today, right? So over the last 400,000 years, carbon dioxide has fluctuated between 180 and 280, 180 and 280 over 400,000 years. And just in the last 150 years, it has gone from 280 parts per million to 420 parts per million. And that's what is causing the problem. So it has changed very, very quickly. And so, that's where that number 1.5 degrees Celsius becomes really important. 1.5 degrees Celsius was the number that was pushed at that meeting, the Paris meeting, by all the small island states across the world. They said that if we were to let the global temperature go up by about 2 degrees Celsius, that means our island nations are going to go underwater. And so we need a stringent temperature target that would save our coastline and save our. And so all the island nations came together. That's called the Alliance of Small Island States, AOSIS. And it's a collective that pushes for really strong, aggressive climate action worldwide. So question 3, right? So I've talked about the indicators of climate change and why these small changes are important. Want to talk a little bit about why carbon dioxide is important. We're talking about aggressive climate action. We're talking about reducing carbon emissions. Why carbon, right? Why do we focus so much on carbon? As all of you know, there are many greenhouse gases in the atmosphere, right? Carbon dioxide is one. Methane is another. Water vapor is a very strong greenhouse gas, and so is nitrous oxide. Right, so greenhouse gases are nothing but gases. They're in trace amounts in the atmosphere, but they are really effective at blocking the radiation that's trying to escape the space. Radiation coming from the surface that's trying to escape the space, right? And in fact, if you look at the strength of different greenhouse gases, water vapor and methane are actually really strong greenhouse gases. And yet we think a lot more about carbon dioxide. And so I'm just going to spend 5 minutes to tell you a little bit about why CO2 is important. What this figure is showing you is a measurement taken at Mauna Loa in Hawaii of CO2 concentrations in the atmosphere. Now, you might wonder that is it okay just to measure carbon dioxide in just one place across the world and say anything definitively about how it's changing? It's okay, because what happens is once you emit carbon dioxide in the atmosphere, it mixes. It's called a well-mixed greenhouse gas. It mixes very quickly because of winds and other circulation features, and it goes everywhere. So it doesn't matter where we emit carbon dioxide. The US might emit carbon dioxide, China might carbon dioxide, India might do it. Eventually, it's going to be everywhere. It's going to affect all of us, right? So that's the one important thing. That makes it easier for us to monitor, right? Because in one place you can measure it, and you know exactly how it's changing. The other feature that you see there, it's very clearly going up over the last 60 years. But the other feature that you see is it's going up and down, right? It's going up and down pretty much every year. And you can imagine why that is, right? That's because during Northern Hemisphere winter, when we do not have vegetation, more of that carbon stays in the atmosphere. Now, spring and summer, everything is going to green up, and that's going to draw down that carbon dioxide. So you see that seasonal cycle quite clearly. But the most important thing about carbon dioxide is that about half of the excess carbon emitted by human activities every year stays in the atmosphere. So when we emit 100 units of carbon dioxide, about 50 units of that is taken up by land vegetation through photosynthesis. The remaining half gets 25% is taken up by land vegetation, 25% is taken up by the ocean, because carbon dioxide dissolves very easily in water, right? So it takes up by the ocean. But the remaining 50 units of carbon dioxide is going to stay there for a very long time, thousands of years. And that makes carbon dioxide really, really important gas to think about. Not going to spend a lot of time on this, but I just want to point out that there is a natural carbon cycle, right? The carbon in the climate system is being transported between, as I said, between the atmosphere, the land, and the ocean. It's being cycled between those components of the system fairly quickly. And that's, if you add it all up, that's about 42,000 gigatons of carbon. But there is a lot more carbon that is stored in the rocks, right? Rocks have millions and millions of gigatons of carbon. And putting that carbon in the atmosphere is very tough. It only happens through volcanic eruptions, right? That's the only way to take up carbon dioxide naturally and putting it in the atmosphere. And the way it goes back into the rock reservoirs is through what we call weathering. That's carbon dioxide in the atmosphere dissolves in rainwater. The rainwater eventually flows to the ocean. That ocean is going to take that carbon into the deep ocean, and eventually it's going to become part of the ocean sediment. And over time, with lots of heat and pressure, it's going to turn into rock, right? You can imagine that process takes a very long time. It takes millions of years. And so those numbers right there tell you 0.1 is 0.1 gigatons of carbon that's transported between rocks and our other reservoir every year. What we are doing is we are digging up, our fossil fuels is basically digging up all that carbon that is being stored in the rock reservoir for millions of years, burning it and putting it in the atmosphere, right? And the rate, the fossil fuels, you can see that red arrow, that rate is about 80 times faster than the natural rate of carbon exchange between rock reservoirs and the atmosphere, right? So combustion of fossil fuels is digging carbon that is otherwise not accessible and putting it in the atmosphere. We have no other natural way of taking it down and sequestering again back into the rock reservoirs. And that's where the problem is. And all of this is not news. I mean, there is so much discussion about whether climate change is happening or not, whether it's caused by human activities or not. We've known this for a very long time. And what I'm showing here is John Tyndall in 1859 wrote that the atmosphere admits of the entrance of solar heat, but it checks its exit, and the result is a tendency to accumulate heat at the surface of the planet. 1859, Eunice Foote was actually a scientist in Connecticut, and now we know that she was the first one to do experiments on the greenhouse effect and tell us about how it works, right? But we've known this for almost 200 years. Svante Arrhenius, a Swedish chemist in 1908, he said that if the quantity of carbonic acid in the air should sink to 1/2 its current percentage, the temperature would fall by 4 degrees. And if the quantity of carbon dioxide goes up, the temperature would go up. 1908, we knew that if we put more carbon dioxide, the planet will warm up. That's the news article from 1912, coal consumption affecting climate. And that's from 1956, Gilbert Klaus, Science in Review, warmer climate on Earth may be due to more carbon dioxide. So it's not the chemistry, the physics is quite simple. The first order physics is quite simple. We know that if we put more greenhouse gases, especially carbon dioxide, the Earth will warm up. And so that helps us with thinking about global policy. And I apologize for this really complicated looking figure, but it's actually quite simple. And it's one of the most important figures for global climate policy. And what it shows you is that how much carbon dioxide is accumulating in the atmosphere, that's along the x-axis, and how global average temperature is changing, that's along the y-axis, right? So what you can do is you can say that I want to limit my global temperature rise to 1.5 degrees Celsius. You can pick that number from the left-hand side. You can draw a horizontal line to that colored area, and then you can go down and find out how much carbon we are allowed to emit if we want to limit the temperature rise to a certain value. That gives you that's the carbon budget, right? So when people say that we have only these many gigatons of carbon left to emit, that information comes from here. It also helps us understand how we're going to do this, right? Because you can imagine that we are 2023 already, and we are somewhere over here. We've already emitted that much carbon, and the budget to emit carbon to keep the temperature to 1.5 C is very, very small. The important question is, how are you going to distribute that carbon budget across the world, different countries? And so just want to say that, when you think about cumulative emissions, I'm just going to skip to the next one. Since the emitted carbon dioxide stays in the atmosphere for a very long time, we can't just blame the countries that are emitting the most carbon right now. We also have to think about what has happened in the past, right? If certain countries have emitted a lot of carbon, that is still there, that is going to be there for thousands of years, and that's going to affect our temperatures. What this shows you that rich countries, including the United States, Canada, Japan, and much of Western Europe, they account for just 12% of the global population today, but are responsible for 50% of all the planet warming greenhouse gases released. And so when John Kerry, our climate envoy, not anymore, went to Africa last year, and he told the Africans that they should be thinking about reducing their carbon emissions. And they were like, who are you to tell us about mitigation and carbon emissions when you are not doing enough and you've already emitted a large percentage of the carbon dioxide? And so global climate policy is all about, it's really complicated right now. It's a contentious topic because rich countries might want to dictate how we should do this, but the developing countries say that, we are still developing and we need energy, and that energy, if it's coming from coal is cheap, we're going to use it right now because that makes a huge difference for certain section of the people in our country, right? And so it becomes a really complicated situation during these negotiations. So where are we heading, right? And this just shows you how global greenhouse gas emission might change in the future and how that might affect our global temperatures. So we, of course, don't know exactly how emissions will change in the future, right? It's going to depend on what we do with technology. It's going to depend on population. It's going to depend on how people use energy, and so on and so forth. And so we come up with different scenarios. And the scenario in red there is a very high emission scenario. So if we continue to burn coal throughout this century, then we're looking at temperature rise of over 4 degrees Celsius by 2020. There's a bit of good news there, though, right? 10 years ago, we thought that we were actually on that trajectory. But if you see right here, we've actually moved away from that worst case trajectory towards somewhere towards that the middle emission scenario. That's the good news, right? Because we're no more on that 4 degrees Celsius. So if we were to follow our current policies, then the temperature would rise by about 3 degrees Celsius. That still has impact. Below that, you have pledges and targets, and those numbers are based on countries indicating what they're willing to do. So different countries are pledging that this is how they're going to decarbonize their economy. And if they were to follow that, then we would get to about a little over 2 degrees Celsius. Now, you have to remember that those pledges, they're not legally binding, right? They're just pledges. They can not follow those pledges, and we cannot hold anyone responsible. And so we will see how that goes. But then there are two interesting pathways, right? And talking about 2 degrees Celsius and 1.5 degrees Celsius, you can see that we need to start decreasing our emissions rapidly now, and then continue with that throughout the century. And for the 1.5 degrees C pathway, you see that the line goes below zero. What that means is you're talking about negative emissions. Now, what does that mean? Negative emissions. That means you are removing more carbon dioxide from the atmosphere than you're putting in, right? And so that's the technology that we do not have. That's just a dream scenario that we would like to follow. We don't have that technology yet. We don't know how to do it. But that's the aggressive pathway that we'll have to follow. And so we're going to need a lot of work globally to be able to do that. And I just wanted to show you this meme because we all are always thinking about what we can do about climate change, right? And we're going to recycle, we're going to drive electric vehicles. But if our governments and our corporations don't act, if they don't make certain things available, there are limits to what we can do. Lots of those little guys will have a huge impact, yes, but it's not going to change unless government corporation policies change over time. And so the final thing, I'm going to go through this quickly because we're already time there. So I'm going to do this in about 5 to 7 minutes, but I want to talk about how this whole global climate change is affecting us here in New England. The first thing you'll see is if you look at the temperature change in the US, this is the map of temperature change in the US over the last 120 years. What do you see? If you look at the eastern half of the US, it's quite clear that something unique is happening in the Northeast. Northeast is warming really fast, and it's not just the Northeast, but it's the coastal region of the Northeast that is warming really quickly. And so I've been working on this for the past few years and trying to understand why is this region warming. And this map shows you how the entire Northern Hemisphere, if you look at land temperatures across the Northern Hemisphere, how much they've changed over the last 100 years. And I just want you to look at bright yellow colors on this map, right? Anywhere you see bright yellow, those regions have experienced over 2 degrees Celsius warming, right? And if you think about just temperature change in summer, only about 4% of the Northern Hemisphere land areas have experienced that level of warming. And that zoom in picture tells you that Massachusetts, Rhode Island, the coastal New England is right in that part. And so why is this happening, right? So our coastal land is warming at a faster rate, but there's something happening in the Gulf of Maine and the Mid-Atlantic Bight region as well. So the ocean, right, adjacent to New England is also warming pretty quickly. And that has to do with changes in ocean circulation. Because one thing you can imagine is as the Greenland ice sheet starts melting and it starts putting this fresh water into the ocean, it changes ocean circulation. And if that ocean circulation changes, then you can have a situation where some of that extra heat that the ocean currents are carrying, it accumulates near the eastern seaboard of the US, and that leads to warming. And there's a connection between these two. So what we're experiencing here on land has to do with changes happening over the ocean. How do you think our temperatures will change in the future, right? And this is a result just for Massachusetts. It shows you that depending on, our temperatures will go up if we continue to emit greenhouse gases, but how much, the magnitude of change is going to depend on the level of greenhouse emissions, right? So in a medium emissions trajectory, the region won't warm as much. Otherwise, it will warm significantly. Now, one of the serious or the most obvious and well understood consequences of warming is that heat waves, for the frequency and the intensity of heat wave, it goes up fairly quickly, right? And so this map is showing you the number of days when we'll have temperature or maximum daytime temperature above 95 degrees Fahrenheit. Now we are right now somewhere over here, right? 2023, that figure goes all the way to 2100. In our current climate, we don't really experience temperatures of above 95 degrees Fahrenheit very much in the region. But if we were to continue emit greenhouse gases in the future, that number will go up significantly. Summers here could have as many as 30 more days with temperatures above 95 degrees Fahrenheit. But if we were to follow a medium emissions trajectory, and I want you to look at the blue curve on the top, on the left-hand panel there, you can see that that number will stay down to manageable magnitude. And so that really highlights the importance of mitigation. If we were to curb greenhouse gas emission, then we reduce the risk of experiencing extreme heat. Extreme heat has, there are other issues related to that. As the air gets warmer, it can also hold more moisture. And so high temperatures and high humidity can make it really uncomfortable. We all know that, right? And so that's another risk, and especially to human health that we have to worry about. The story about how rainfall is going to change, precipitation is going to change, is complicated. We are in a region where our climate or precipitation gets affected by what's happening at northern latitudes in the Arctic, as well as what's happening in near the equator. And so it's a really complicated story. But overall, what we expect is that we will get more, the Northeast climate will get wetter if emissions continue in the future. But still, you have large variations from season to season and year to year. And what that means is that, there might be years in the future where you would have significant, very low precipitation, and you combine that with really high temperatures, and that would dry out soils, and you would have drought conditions. Right? You can remember last year in spring, it didn't rain very much, and then temperatures went up in summer, and that led to a short-term flash drought. But we can also get a lot of rainfall, right, because of that high variability. And that's what we're experiencing right now over the last few months, one of the wettest winters that we've experienced in the region. And so from the planning perspective, right, you can't just say that, oh, it's going to get wetter and we'll plan for that future. Planners really need to think about these short-term variations, because those variations have really large impacts. And then finally, I want to show you, we care about the sea level rise along the coast as well. This shows you data for Boston, and the sea level around Boston has already gone up by about 195 feet, 1 foot sea level rise. And what that small change in sea level rise is doing is that it's inundating our coastal areas more. So it's not just storms that bring in storm water along our coastal areas. It's when we have high tides, what we call sunny day flooding. The day is like, it's like today, but when there's high tide, it pushes all that water in. And that happens just because the sea level has gone up by a small amount. And this is just a picture of coastal flooding that happened in 2018. We had 4 back-to-back nor'easters in March, and that led to scenes like this. Much of our Massachusetts coast flooding again and again in a short amount of time. I'm just going to show you one final thing, and this is the work since we are here and people are thinking about conservation, species conservation. I just want to mention one big effort that I was involved in, and this report came out just last year. It's called the title is Regional Synthesis of Climate Data to Inform the 2025 State Wildlife Action Plans. And so this just shows that state agencies are thinking about the changes that are already happening. They are preparing to release or design wildlife action plans for conservation next year. And to inform their decisions, over the last 3 years, we've worked on creating a database that will help them make adaptation decisions. And so this report has many different chapters. The first one is about climate data and projections. And then many people have worked really hard to understand which species are vulnerable, which species, tree species as well as animal species, bird species are vulnerable to climate change. What are we doing in terms of adaptation? And this report provides case studies for that as well. And my contribution to that was the first chapter, the climate data and projections chapter. And as part of that effort, I've created state-specific climate reports. So some of the figures that I showed you for Massachusetts are from that report that was released last week. So there's a QR code. You can use your phone to capture that, and I can give you that information later. And so I'm going to stop there, and I'm going to leave you with this figure of the emperor penguins looking at the crack in the sea ice and contemplating the future. Thank you so much.